Hey guys, it's Mr. Woodward. This is the Understanding Newton's Cradle worksheet that accompanies the demo of Newton's Cradle. And this is going to be a way for us to organize our thinking around this idea of conservation of momentum and the patterns that we see with these metal spheres. So what we've got at the top is the number of moving spheres, the picture of these spheres before they collide, the total momentum before the collision, the picture after the collision, and the total momentum after the collision. So I'm gonna do the first couple for you, and then you're gonna do the rest. So in this first one, we can go ahead and label all of these spheres with a mass m. So go ahead and put m in each one of them to help you remember that they have a mass of sort of 1 m each. And then go ahead and add a velocity arrow to that first mass to show that it's moving to the right. So in this case, the total momentum before the collision is 1 mv because we have one mass moving at velocity v to the right. And then after the collision, we can again label these each m for mass. And this one now moves to the right with velocity v. And so we can see that the total momentum after the collision is also 1 mv because these guys have no momentum, they're not moving at all. This one has momentum of 1m times 1v to the right. So we get 0 mv plus 1 mv equals 1 mv over here. And I guess you could write the same thing over here as well. 1 mv plus 0 mv equals 1 mv, if that helps you to think about the addition of what happened over here. So let's go to the next one. Now the key is we have to draw two moving spheres, and the total momentum before the collision has to be negative 2 mv. So the negative means moving to the left. So let's go ahead and draw two moving spheres moving to the left, which leaves 3 not moving. So we can draw both of these guys moving to the left with velocity v, and they're going to collide with these 3 masses. So what we have is no momentum from these 3, and 2 masses here moving to the left with velocity v, so we have minus 2 mv is the momentum before the collision. And then the picture after the collision is we know what comes in goes out, and so we'll have 2 spheres moving to the left, leaving 3 behind, and these continue to move to the left with velocity v. So these are minus 2 mv here, plus these 3 have no momentum, 0 mv, gives us minus 2 mv. Let's do one more. Now we need to have 2 spheres moving, but the total momentum before the collision has to be 0. So somehow the momentum of these 2 spheres have to cancel each other out to get 0. So that's going to have to look like this. We're going to have one sphere moving from the left and one sphere moving from the right, and 3 spheres in the middle not moving. So again, these have velocity v. So the total momentum before the collision is 0 because this is 1 mv. These have no momentum, so I can say plus 0 mv. And this has momentum to the left. So plus negative 1 mv equals 0. 1 mv plus negative 1 mv is going to equal 0. And what's going to be the picture afterwards? Well, this sphere is going to transfer its momentum through all the way to the right. This sphere is going to transfer its momentum through all the way to the left. So we'll get a mirror image of the picture. This one will now move left. This one will now move to the right with velocity v each. And so to add this up, we get negative 1 mv is the momentum of this sphere, plus no momentum from these, plus positive 1 mv from here. And that's going to equal 0. Now, see if you can do the rest following the rule that you have to have this number of moving spheres and that momentum has to add up to this. So your task is going to be to try to draw the picture that matches these descriptions and then figure out what the total momentum afterwards is. Don't forget at the very bottom, try to identify this pattern. What can you conclude about the total momentum before and after each collision?